Hello, everyone. It is late today. I went to go see some family, and then I came home and I had to go do some paperwork for some club relations. Um, but now I'm here. It's almost my bedtime, so I'm trying to make this quick. But it is 9:42 p.m. Thursday, June 5th. I think this marks day 11. I believe it's day 11. Um, of coding every day. Um, Today we're gonna make it a fast one because it's late. So let's do it. I think I'm probably just gonna do this one hard, and then call it a day. I still gotta eat dinner and wind down to get ready for bed. So let's go. Largest rectangle in a histogram. So given an array of integer heights representing the histogram's bar height where the width of each bar is 1. Return the area of the largest rectangle in the histogram. Interesting. Okay. See what's happening here. I actually don't have any idea on how to solve this. My kind of first idea is like we'll hold like a max value. So like I'll say like x equals 0. So we have 1, 2, 3, 4, 5, 6. We have 6 here. That's one answer. We have 4 here, and then we have 10 here. I'm gonna use a hint. I'm giving up. Okay, so I can do this in the hint. Alright, so I had a feeling I would just kind of linearly pass through once. So I'm wondering if we can use like a min stack approach. Find like the keep the minimum value at all times. Dude, look at this. Absolute vomit of words. Holy hell. Okay. For a bar with height h, try extending it to the left and right. We can see that we can't extend further when we encounter a bar with a smaller height than h. Yeah. That's like open squared. The width will be the number of bars this brute force approach would go through. It can form by saying towards left and right. This would be in open squared. Can you get a better way? Maybe pre-computing the left and right boundaries might be helpful. Maybe. Pre-computing the left and right boundaries. Min stack? The left and right boundaries are the positions up to which we could extend the bar at index I. The area of the rectangle will be height of the current thing times the right minus the left plus 1. Which is the general formula for the height times width. These boundaries are determined by the first smallest bars encountered to the left and the right of the bar. How can we find the left and right boundaries now? Maybe a data structure is helpful. Min stack? We can use a stack with a monotonically strictly increasing nature, but instead of storing values, we store indices in the stack and perform operations based on the values at those indices. The top of the stack will represent the smaller bar that we encounter while extending the current bar to the left and right boundaries. We perform this algorithm from left to right and vice versa, storing the boundaries. Then we iterate through the array to find the array for each bar and return the maximum area we get. Right, I'm not gonna lie, that is a lot of word vomit for this, but it is a hard, so you know, as kind of expected. You know, hards aren't exactly self-intuitive half the time. We can use a stack with a monotonically strictly increasing nature, but let's see, what exactly does monotonically mean? I know like mono means one, and monotone is kind of like, you know, or monotonic is like one motion, typically. Alright, brother. This stupid AI search is slowing stuff down. But instead of storing values, we store indices in the stack and perform operations based on the values at those indices. The top of the stack will present the smaller bar that we encounter while extending the current bar. Okay, I'm... He wants me to make a stack that's like... For everything to be strictly greater than the thing before it, that means it's sorted. No? Okay, so 3 has to be strictly greater than everything below it. And then 2 has to be strictly greater than everything, or... Yeah, than everything below it. And 1 has to be... Yeah, so like that's just sorted. Brother, what? Okay. Oh! Okay. So I don't need to keep all the values. What? Alright, so... I'll say monotonic left, right, left to right, and then monotonic right to left. Okay, actually, I might need to draw this out first, so that way I truly understand like what's going on. Because I hear you, but I don't see you. I hear you, but I don't see you. Okay, so we're gonna have LR and RL monotonically increasing. So we have 2, 1, 5, pop it, 5, 6. We have 2. Oh, audio recording? Yeah, it is. Okay, dope. Thought I should unplug it. Then we pop these. Put a 2, 3. Strictly increasing, does that mean like the same doesn't count? I don't know. Okay, and then we have 3, pop it, 2, pop it. Wait. 3, pop it, 2, 6, pop it, 5. Pop it, 1, 2. Is that what we're talking about? I don't think that's what we're talking about. Is it the top? To me, it seems like the top of the stack is just going to be the last thing, regardless. I don't. Yeah, I don't know.
Let's solve LeetCode 84, largest rectangle in histogram. So we're given a bunch of bar heights, and each bar has a width of 1. We want to find out what's the largest rectangle we can get and return the area of it. So in this case, the largest has an area of 10, width of 2, height 5. Another rectangle we could get has an area of 8. This one has a width of 4, height of 2. Another one has a width of 6, height 1, so area 6. There's also other rectangles we could get, but these are a few of them. So if we just draw the first two bars, let's see if we can notice any patterns from them. So if you look at them, the first one is bigger than the second one. That means for this rectangle of height 2, we can't extend it any farther. Once we reach this 1, we can't extend it any farther. So the biggest rectangle we could get with height 2 is just this one right here, because there's a little hole over here, so we can't push it any farther. But for this 1, we can push, since the height is 1, we can kind of extend it towards the left a little bit, right, and use the left rectangle. And since we can't extend the height 2, we can still extend the height 1, because there's nothing coming after it that'll stop us just yet. Let's look at the opposite scenario. What would happen if the 1 came before the 2? In this case, the 1 comes first, so we can keep extending it to the right. There's nothing stopping us, right? And the 2, there's nothing coming after it just yet that'll stop us, so we can actually extend this height of 2 a little farther, because there's no smaller height that comes after it, so there's no hole, right? The third case is if two rectangles were even right next to each other. In this case, we can also keep extending it, right? Because there's no hole. These rectangles are the same height. There's no smaller rectangle stopping them from being extended farther to the right. So this tells us that the current heights are going to be in increasing order, because this 2 cannot be extended beyond this point. So we can only compute the area of height 2 from this width, and then we have to pop it, right? We can't extend it any farther, so we have to remove it from being considered. So now let's look at the case where all the heights are in increasing order. Notice how since they're all in increasing order, they can be extended to the right continuously, right? So this 1 over here can continue to be extended to the right. This 2 can be extended to the right. This 3 can be extended to the right. And this 4 can be extended to the right. None of them can be extended towards the left though, right? Because the height to the left is smaller, so they can't be extended to the left. But what would happen if we introduced a smaller height after? So if we introduced a 3 over here, that would mean that this 4 over here, it can't be extended any farther because there's a 3 coming after it. So all we can do is say, okay, these are the boundaries of height 4. Let's compute the area, which is going to be 4 in this case because the width is 1, and then we have to remove this from being considered, right? So we pop it. What if we introduced a 2 instead? Well, the same thing will happen. We can't extend this 4 any farther, right? So all we can say is these are the boundaries of it, right? We started back here, and then we extended all the way until we got to this 2. So compute the area, and then pop it, right? Let's look at this 3 now. We can't extend this any farther either, right? Because the 2 is less than the 3. So we can say that these are the boundaries of the 3. Let's see what the area it could have contributed was. It's 6. Maybe that's the max area. We don't know yet. But we know we can't extend this 3 any farther. So we have to pop it as well. What about this 2 over here? Well, since the new height that we got is also 2, we can keep extending it. There's no reason we can't. So we will only have to pop these 2 elements, the 3 and the 4, because we can't extend them any farther because now we reached a 2. Let's look at one last example to drive this point home. So now we have a 1 over here, right? So we can't extend the 4.
So like whenever I'm popping, do I save that? So it's like... F2. Oh, strictly increasing. So 2 gets popped. Drop a 1. So 2 gets popped. I'm going to store that over here called 2. Okay, then I have 1, 5, 6, 2. Alright, so this is going to pop 5, 6, which is 10. So 10 comes from 5, 6. Okay, I'm going to put 2 here. And then I'm going to put a 3. Alright, and then I can like run the algorithm on here to see three. Then I added 2, so I'm gonna pop that. So I'm gonna drop a 3 here. At the 2, at the 6. Oh, but then I have 5. 5 is gonna pop the 6, so I'm gonna drop a 6 here. Oops, we drop a 6 here. Go to 5, and then now I go to 1. That's gonna pop the 5. Oh, that's gonna pop the 5 to the 2. Okay, interesting. No! Fuck! Sorry with the language.
And then we extended all the way until we got to this 2. So compute the area and then pop it, right? These two elements, the 3 and the 4, because we can't extend them any farther because now we reached a 2. Let's look at one last example to drive this point home. So now we have a 1 over here, right? So we can't extend the 4 anymore either. So we compute the area, 4, and then remove it from consideration. Also this 3, it can't be extended any further. So we compute the area, 6, and then remove it from consideration. In this case, even the 2 can't be extended any further, right? Because the 1 is too small. So we compute the area, in this case, 6, and then remove it from consideration. So in this case, we had a 1, and then we popped 3 elements from consideration, right? So notice how we are popping elements, and we're only popping the most recent elements. We're not popping an element that's in the middle. We're only popping them from the top to the bottom, from the most recent elements, right? So that tells us we should use a stack for this problem. So the stack will contain the current heights that we are considering, and we'll pop them from the top when we are no longer considering them. So now let's look at the algorithm. So I have a stack, and in the stack, I'm not just gonna hold the index, and I'm not just gonna hold the height, I'm gonna hold both of them at the same time. So I'm holding the start index and the corresponding height. I'm also gonna be maintaining what the max area when we are no longer considering them. So now let's look at the algorithm. So I have a stack, and in the stack, I'm not just gonna hold the index, and I'm not just gonna hold the height, I'm gonna hold both of them at the same time. So I'm holding the start index and the corresponding height. I'm also gonna be maintaining what the max area is so far. So now let's start at the beginning of the array. We get element 2. So since there's nothing in the stack, we can't pop anything, let's just add it. So at starting at index 0, we have a height of 2. Next, we get to index 1, there's a height of 1 over here, right? So now we're gonna add the height 1 to our stack. But let's look at our stack. There's a height 1 that's at the top of the stack right now. That means that this 2, it can't be extended any farther. We reached a height that was smaller than the 2. So that means we're gonna pop the 2 from the stack. But before we pop it, let's just see what's the max area we could have gotten with this 2 height. So it started at index 0, right? We can see it started at index 0, and we just reached index 1, so that's the range of the width, from 0 to 1. So the width is 1, the height is 2. So that means the area is 2. So far, we'll say our max area is 2 now. And now we can pop the 2 from the stack. So what's the index of this 1? Now, well, we're currently at index 1, right? So we can say that that's the index, but I'm actually gonna do it a little differently. If you look at this 2, we can actually extend this 1 all the way back because we just popped this 2. That means this 1 could have been extended back by 1. So instead of saying the index of this 1, of this height 1 starts at index 1, I'm gonna say it starts at index 0 because we can extend it all the way back to the 0 over here. Next, we're gonna get at index 2. We have a 5, right? So we'll add that to our stack.
Yeah,
the 5 is greater than the
that?
1. So there's no restriction. This 1 can still be extended. So I'll just add the 5 and the corresponding index, which is 2, to the stack. Don't need to pop anything. Next, we get to index 3, right? There's a height of 6. Again, this 6 is greater than the value at the top of our stack, which is 5. So the heights are in increasing order so far, which is good. That means we don't have to pop anything. And the index we reached the 6 was at 3. That means this 5 can continue to be extended. That's why we don't have to pop the 5. Now we get to index 4. This is where the interesting stuff happens. At this index 4, we have a height 2. The problem is this 6 now can't go any farther. We reached a 2. So this 6, which started at index 3 over here, ended up stopping at index 4. That means its width was only 1. So we have to pop it now, but before we pop it, let's get the area that it could have made. So the width...
Hold on. Oh! Because it could go left. How are you always so sure? How do you stay certain about that? Oh, because you just take the left.
is 1, the height is 6. That means the area it could have made is 6. This is the max area that this height of 6 could have created. So we'll update our max area. 6 is greater than 2. Our max area is now 6. And let's pop this 6 from the stack. Okay, now the top of our stack is 5. But wait, 5 is greater than the 2 as well. That means this 5 can't be extended any farther. So we look at the start index of this 5, it was index 2, and we stopped it all the way at index 4. So that means its width was 2, its height is 5, so the area it created was 10. So before we pop it, let's just compute the max area that it could have created. It's 10, so we update our max area. Our max area is now 10 greater than 6, and we remember to pop this 5 from our stack. Now we look at the top of the stack, it's 1, right? 2 is greater than 1, so we don't have to pop this 1, because this 1 can continue to be extended, so we don't have to pop it, right? And what about the start index do we put for this height of 2? Can we put index 4? Well, yes, we can, but we notice that we just popped 2 elements, 6 and 5. That means this 2 can actually be extended backwards all the way to index 2, right? So instead of saying index 4 is the start value of this 2, I'm going to say index 2. Next we reach index 5, the last element. So this height is 3. Let's put it on our stack. We see 3 is greater than 2. That means we don't have to pop the 2 from the stack. That means that this 2 can continue to be extended. There's no need to pop it. And what about the start index of this height 3? Well, we can't extend it backwards anymore, so I'm just going to say the start index is 5. If you look, we still have 3 elements left in our stack. So what do we do with them? So we have 3 elements that we didn't end up popping from the stack. What that tells us is that we were able to extend them all the way to the end of the histogram. So we still need to compute the areas we could have created from these heights. So let's iterate through them and figure that out. So
Oh, you can't see it right there.
let's start at this last one. At index 5, it started and it had a height of 3. So it started at index 5 and went all the way to the end of the histogram. So that means the length of it was just 1. The height is 3, so we can compute the area as having an area of 3, right? Now this area of 3 is not greater than our current max of 10, so we don't update our max. Let's go to the next element in our stack. It's index 2, height 2. That means it started at index 2 over here, and it went all the way to the end of the histogram, and it had a height of 2. So that means the width was 4, the height was 2, 2 times 4 is 8, so the area it created was 8. Eight is not greater than our max area either. The max area is 10, so we don't update the max area. The last element in our stack, index 0, height 1. That tells us it started all the way back here at index 0, and it extended all the way to the end of the histogram. So from 0 to the end is a width of 6. The height was 1, so that means the area it created was 6. This 6 is not greater than our current max area of 10 either, so that means the max area at the end is 10. So that's the result, 10. So with this algorithm, we only had to iterate through the histogram once. We had to push elements onto our stack, but we had to only push each element once and pop it once. So that means the overall time complexity is big O of n.
Okay. Interesting. Mosquito bites are getting me bad, man. Holy. So if the stack is empty, then we're just going to have to push no matter what. She's doing it right. In case I have to edit it. So that means if it's greater than or equal to, we'll be fine. So while the monotonic stack of -1, 1, so we need the distance, so that's index minus that is the distance we'll get. My goodness, it's late. So it pops it, get the latest index, and then I'll set it to the latest index. I'll say if this works, I'm gonna clean up because it's not clean. So I'm gonna run this. It's not the correct solution because I still haven't done my iteration, but it should at least give me case one. Yeah, that. So it should at least give me that, right? Now I'm gonna do my iteration. infinite loop because I didn't delete from it. Oh, the issue is I wasn't spelling it right. And I'm still not spelling it right. Monotonic. Monotonic. Man, I didn't spell it right at all. Okay, perfect. It runs. I'm just going to do a little bit of cleanup. I'm going to basically say... And that should clean it up. Nice. Submit it. Uh-oh, it's a little slow. A little sluggish. Time limit exceeded. Ugh. I mean, like, I'm just gonna have to look at the solution, really. Oh, a divide and conquer? This is not run without the optimal solution. See if that runs the optimal solution. Maybe a for loop is faster. Oh, that did it. Nice. Cool beans. All right. I'm gonna call it there. It's late, way past my bedtime. I'm tired, and I'm gonna have a very sleepy day tomorrow. It was a short video. I kind of had to hit my way all the way through. I mean, those hards are pretty difficult, but, you know, if you can kind of sit and stand with it, you can get a little bit of understanding of, mathematically speaking, what's going on. That was a cool problem. A difficult one, but a cool problem nonetheless. 29 LeetCodes codes completed. 3 algorithms finished up. And it's day 11, right? So, pretty good pace, because I have like 60 days overall to do it, so, you know, getting, what is that, I'm getting around 3-ish done per day. I'll say 2. Do the low ball, two per day. So, still need to do quite a lot more, but we'll get to it. Anyways, thank you for watching, and I'll see you tomorrow.